So in the last couple sessions, we've been talking about how to measure some of the properties of stars. We talked about measuring distance using that parallax method. We talked about how if I know the distance and the apparent brightness, I can figure out the luminosity. We said if I know the temperature as well as luminosity, I can figure out the size of the star. And we talked about how if I have a bunch of stars orbiting around each other, we can use those orbital properties to measure the masses of those stars. What I want to do in this session is go into a little bit more detail on how we measure the temperature of these stars. We've talked earlier in the course about Wien's law, saying if I know the wavelength of maximum emission in nanometers, then I can use Wien's law to figure out the temperature in Kelvin. Basically saying that depending on where that wavelength of maximum emission occurs, we can determine the temperature of the star. So if I have wavelength versus intensity, then for a low temperature star, the graph might look like this. And for a higher temperature star, we have wavelength versus intensity again. For a higher temperature star, that wavelength of peak emission will be shifted to shorter wavelengths. So this would be lambda max over here. And this would be lambda max for this one. We'd have the low temperature star, and we'd have the higher temperature star. So again, if we have that wavelength of maximum emission, in this case, it looks like it's around 4,650 angstroms, which is 465 nanometers. We're going to see some of these wavelengths in angstroms. So just to remind ourselves, if we have, for every 10 angstroms, that's equal to 1 nanometer. Okay. Just so you know that this is just another unit of distance, divide by 10 to get the wavelength in nanometers. So if I know that wavelength of maximum emission, and I have Wien's law, I can calculate the temperature of this star. The problem is, and I mentioned this in one of the earlier sessions, this effect of interstellar reddening. Empty space is not entirely empty. It has little bits of gas and dust in there, and that dust will have the effect of preferentially blocking more of the blue light and letting more of the red light through. So more of the red light gets through than blue light when the light passes through this. Again, very, very, by any means that we've talked about on Earth, space is a vacuum. But there is still just a little bit of dust and gas in interstellar space. And this causes this interstellar reddening or extinction. When we're looking at the spectrum of a star, if this is the spectrum of the star that was originally given off by the star, interstellar reddening can have the effect of blocking a little bit more of the blue light than it does of the red light. And that can have the effect of shifting the apparent position of the wavelength of maximum emission. And if we don't account for this, if we don't find other ways to determine the temperature, this could throw off some of our results. So what we want to do in this class is say, in this session, is say, is there another way that we can get a more reliable measurement of the temperature of a star? And the basic idea is going to be that even though all of the stars that we're going to talk about have pretty much the same composition, around 3/4 hydrogen, 1/4 helium, and 2% heavier stuff, depending on the temperature of those stars, different spectral lines are going to become more or less prominent. So let me write a little bit of that down. So all stars, approximately 3/4 hydrogen, 1/4 helium, and 2% heavier stuff. Again, there is variation from star to star. We're not going to look at that much detail in the composition right now. But most stars are around 3/4 hydrogen, 1/4 helium, and 2% heavier. And depending on their temperature, so depending on temperature, different spectral lines will be more or less prominent. So different spectral lines will be more or less prominent. And if we can identify these patterns, we can use the strength of those spectral lines to identify, well, what is the temperature of this star? We're going to be looking at some stellar spectra, and you can access some of these spectras at this website, skyserver.sdss.org. This is an absolutely massive repository of astronomical observations. This is every night. This is taking more data and increasing the size of this survey. They have measured the basic light properties of many hundreds of millions, I think over a billion individual objects, just measuring their individual kind of general light properties. And they have high accuracy spectras of, I think, coming up on over like 10 million individual objects. Definitely in the millions of objects. This is a huge repository of information. I think there's somewhere along the lines of almost 1,000 terabytes of information that's freely available. People do research with this website, research that gets published. So we're going to be looking at some of those spectras today. So let me bring that back up. So again, some of the basic ideas that we're going to be talking about. All these stars have basically the same composition: 3/4 hydrogen, 1/4 helium, and at most around 2% heavier elements by mass. And depending on the star's mass and its stage of evolution, these stars can have different surface temperatures. We're going to talk about stellar evolution in the next couple sessions. But again, depending on the temperature of the star, these objects may be, depending on the temperature of the star, certain spectral lines are going to become more or less prominent. We're going to talk about some of those patterns and where those patterns come from and how we can use those patterns to accurately measure the temperature of stars. So we'll be using this OBAFGKM scheme for classifying the stars. Once again, as just kind of a general picture, we are still going to be looking at things in terms of Wien's law. If I have the spectrum of these two stars, Rigel and Betelgeuse, if I was to map out the overall shape of these spectras, something like that and that, then we can kind of use Wien's law to get a pretty good estimate of the temperatures of these objects. This graph shifted very, very far to short wavelengths. That wavelength of peak emission is only 252 nanometers. It's not even on this graph. So that would correspond with a very, very high temperature star. Whereas the star Betelgeuse, well, its spectrum, if we kind of map that out, more of that light is being given off at longer wavelengths. So the surface temperature of that star is a little bit cooler, 782 nanometers. So it's going to a lower temperature. So I recommend, again, just as some practice, pause the video and try to use Wien's law to calculate the temperatures of these two stars if this is the wavelength of max emission. So take a minute to do that. Okay, and if you plug in the numbers, for Rigel, you should get somewhere around 11,500 Kelvin, so a very high temperature star. Remember, for comparison, our sun's temperature is around 5,800 Kelvin. So Rigel is a pretty high temperature star, whereas Betelgeuse, its temperature is only around 3,700 Kelvin. So significantly lower temperature than the surface of our sun. But again, what we want to focus on for this session is the fact that at different temperatures, different elements will be more or less efficient at producing their spectral lines. So these figures that we've looked at, like, let me kind of go back to a couple of these. These graphs that we're looking at, we get this rainbow of colors with a few dark bands. And when we look at them, if we look up through the spectroscope, it would look something like this, a rainbow of colors, but it's missing a few bands of colors. what type of a spectrum, think for a second, what type of a spectrum would that correspond with? Yeah, if we have that rainbow of colors, but it's missing, it has a few dark bands in it, that would be an absorption spectrum. All the stars that we're going to look at are going to have absorption spectra. So we have this classification scheme that's ordered in kind of a weird way. They're ordered by letter, and this is the classification scheme. From hottest to coldest, so this would be the hottest, to coldest. This would be O, B, A, F, G, K, and M. There are a number of different, I don't know the exact historical reason on why these letters were given to these stars, but there's a lot of mnemonics that you can kind of develop for remembering this. There's O, be a fine girl or guy, depending on your preference, kiss me. So O, be a fine girl, guy, kiss me. Some others that I like are one big and ferocious goat killed me, or overseas broadcast, a flash, Godzilla kills Mothra. You can probably come up with your own mnemonics if you want, but again, we have this OBAFGKM sequence. These are subdivided even further by number, going from 0 being the hottest of that particular spectral type, of that letter spectral type, to 9 coolest. So if we have a type A star, the hottest one would be A0, then A1, then A2, then A3, all 4, up to 8, 9, and then we'd have F0, F1, F2, all the way up to the G. That would be in order of decreasing temperature. So in this case, a G8 star is hotter than a G9 star is hotter than a K0. If we have the G0, 1, 2, all the way up to 8, 9, and then K0. K1, K2, all the way up to 9 for that. So what we want to identify is what happens to different elements at different temperatures, and how does that affect which kind of materials are going to be very efficient at making strong spectral lines. Maybe before we talk about this, I should talk about what we mean by a strong spectral line. Because imagine that I have an absorption line that looks something like this. We have this spectrum, and then there's a little bit of an absorption line, a little bit of a spike down in that graph. Okay. That little spike down, that would be a weak spectral line. Again, there is a spectral line there. Some of that light, that particular wavelength of light, is being removed from the sample, but not very much. Right? So if we have a spectral line, one of those downward spikes in the graph, if it's just a little spike, we'd call that a weak spectral line. On the other hand, if we had something that looks like this, where that spike goes down really, really far, that would be a strong spectral line. We're not going to talk about the exact details on how deep is that spectral line and what is strong, what is medium, what is weak. The level of detail that we're going to use for this course is going to be pretty approximate. Again, there are very detailed calculations that you can do to figure out exactly how deep is that spectral line, exactly how much of that material is there, exactly how much does it match up with that ideal temperature. We're not going to look at it in that much detail. We're going to do more of an approximate view in this case. So what we want to know is what happens to different elements at different temperatures. And overall, we're going to have this kind of a picture on how strong are each of these different kinds of spectral lines for different spectral classes. So let's talk about some of these. At very low temperatures, the lowest temperature stars that we have, where their surface temperatures are in the around 3000 Kelvin. At those temperatures, molecules can still exist on the surface of this star. So you're going to get features owing to molecules if you have one of these relatively low temperature stars. A little bit if you have a type K star, more if you have a type M star. So this graph on the left side of the screen, this is saying at lower temperatures, when we go to these low temperature spectral classes, those molecular absorption features are going to become more and more prevalent. We're going to see them more and more easily. The reason that we don't see them at higher temperatures is if I have a molecule is a set of atoms held together by chemical bonds. So for example, water is H2O. It's an oxygen atom connected to two hydrogen atoms. Well, at high temperatures, those molecules will start to vibrate and shift around, and eventually at a high enough temperature, those molecules will break apart. So at low temperatures, we see absorption features owing to molecules, but at higher temperatures, those molecules have broken apart and we don't see those features anymore. In this kind of a range, from around G to, a little bit in M, a little bit in F, but mostly around G and K, that's when neutral metals, things like the sodium line and the magnesium line, we're going to talk about specific lines that we're going to use as reference points for these. These neutral metals are going to show strong absorption features. So those happen around still pretty low temperatures. But at higher temperatures, if I have a neutral atom where we have the nucleus in the middle and we've got electrons going around it, and the number of electrons match the number of protons in that nucleus. Well, if I go up to higher temperatures, those electrons are going to get excited. If I increase the temperature too much, some of those electrons are actually going to be ripped away from the atom and leave us with ionized metals. So again, at somewhat higher temperatures, now ionized metals are going to become more important. And for those ionized metals, to kind of reference that, we're going to look at what are called the H and K lines from ionized calcium. These are just certain spectral lines that are prominent in the spectras of a lot of stars. So the stuff that I have on this diagram, the parts up here saying sodium and magnesium, Na for sodium, Mg for magnesium, these H and K lines of ionized calcium, this is going to identify where on the graph should we be looking for these features when we start looking at these spectrals. So at higher temperatures, those metals are going to become ionized. So we're going to see those features more strongly. At even higher temperatures, well, the hydrogen series, the hydrogen spectral lines are going to become more and more important at higher temperatures. The reason why we don't see these hydrogen features at lower temperatures is because at lower temperatures, the electron that's orbiting around the hydrogen atom, at low temperatures, that electron is just going to be happy staying in the ground state and just not interacting with anything else. If I want to get the visible spectral lines for hydrogen, I need to actually raise the temperature of that hydrogen high enough so that the electron is out of the ground state. So if we want to get these visible spectral lines, I have to have a high enough temperature to get those electrons out of the ground state. But if I raise the temperature too much, to a very, very high temperature, those electrons, again, are going to leave the hydrogen atom, and then there's no electrons left around hydrogen to actually make more of these spectral lines. And at really, really high temperatures, the hydrogen is completely ionized, there's no electrons left, and now helium is going to start to leave its ground state and give us some visible spectral lines. So this list, and again, we're going to talk about parts of this in more detail as we start actually seeing some of these features. This set of properties is kind of described in this particular graph, saying at lower temperatures, molecules become more and more important. those molecular absorption bands. Around type G and K stars, those neutral metals are going to be really important, are going to show strong spectral features. Around class F and class G, those ionized metals are going to show strong features. Around type A, that's where you get the strong hydrogen features. So this graph will be given to you on the test. I do not expect anyone to memorize all of these things and memorize the exact patterns. So this graph will be given on your test as you're doing homework questions based on identifying these spectral features. Use this graph to help you identify what spectral class we're dealing with. So I think it's high time we actually look at a spectrum and see how we can identify the spectral features, and then use the strength of those spectral features to identify what spectral class we're dealing with. So this is the spectrum of a star very much like our sun. Okay, this isn't the sun itself, but it's a star like our sun. Again, this is an absorption spectrum. We would get this if we sent this light through a prism. I mostly see all sorts of different colors of light, but every once in a while there's this downward spike and we get one of those dark lines. So a little bit of a downward spike here, a little bit of a downward spike. We see some of those spectral lines at those particular locations. And on these graphs, the different spectral features are going to be listed near the top. Notice we have sodium and magnesium right there. That's going to be our neutral metals. Notice we have hydrogen alpha, hydrogen beta. It's kind of hard to read on that one, but there is a hydrogen beta in there. Hydrogen gamma, hydrogen delta. That would be the hydrogen series. We're going to identify whether those features are strong or weak. We have the H and K lines. Right here, we have those H and K lines of ionized calcium. The strength of those lines is going to tell us how much are we getting in the ionized metal part of the spectrum. Okay. So again, these specific spectral lines are ones that are commonly found in stars. So we use those as kind of our reference points for, do we see features from hydrogen? Do we see features from ionized metals? Do we see features from neutral metals, to help us identify what is the spectral class of this star? So let's kind of go through this. We've got our hydrogen series of absorption lines. Again, sorry that this one's kind of hard to see with the hydrogen beta. Again, each of those show up at known wavelengths. So when we looked at the spectrum of hydrogen, that red line that we saw, that was the 656 nanometer line. The bluish line, that was at 46 nanometers. The one that was looking more purple, that was 434. It was kind of hard to see this last one. This last one's around 406, I think. I can't remember that one exactly. But we've got those hydrogen lines. And again, some of the other lines that we're going to be focusing on are the sodium and magnesium lines for that ionized metals, and the H and K lines. So again, we've got magnesium. There's actually two lines that are really close together for magnesium. Sodium also has two lines that are really, really close together. And this singly ionized calcium, those H and K lines, are on this part of the graph over here. Again, when we're trying to identify what kind of a star this is, we want to use this graph, and the strength of that absorption line relates to how far down the spectrum dips at that particular wavelength. If we were looking at an emission spectrum, the strength of the spectral line would be how high upwards does that graph spike at that particular wavelength. So what we want to do is try to look at the spectrum of this star, identify which features are strong, which features are weak, and also which features are missing. Because all of those pieces of information will allow us to identify, well, what kind of star is this? Another thing that I want to point out is when we talked about the composition of these stars, all of these stars have pretty much the same composition. 3/4 hydrogen, 1/4 helium, 2% heavier stuff. Just because a spectral line isn't showing up very strongly in this spectrum doesn't necessarily mean that this star is missing that material. Or if we get some really strong spectral features, it doesn't mean that the star is particularly made up of that particular element. It just means that if we get those strong features, the star is at the right temperature for those features to be prominent. It takes a lot more calculation stuff beyond the scope of this course to actually use that information to figure out, well, how much of that particular element or that particular material, how much of that is in the surface of this star. Okay? So that's going to be beyond the scope of this course. And again, this graph is what we're going to use to identify all of those spectral lines. So let's go back and look at this, this graph. The way I like to do this is to make a list of features. You know, the overall temperature from Wien's law, looking for hydrogen features, are they strong, weak, or not there? Looking at ionized metals, is it strong, weak, or not there? Looking at those ionized metals, those H and K lines, and we'll talk about the molecular bands a little bit later. But let's go through this one. So the Wien's law temperature. This graph, if it peaks around here, that's kind of a medium temperature star. We're going to see other cases. Sorry, the wrong thing. We are going to be looking at cases where some of those stars peak way, way over here, or some of them are going to be off the scale to the side. Other stars are going to have graphs that look something like this. This one is kind of mid-ish range. So we're going to say that that Wien's law temperature, that's going to be medium. Okay. So medium temperature. Now let's look at each of those features. For that hydrogen series, again, we see these kind of downward spikes. They're, I'd say, weak to moderate in this case. Some of them are going to be a little bit difficult to see, but I'm going to call those, you know, weak to moderate. Weak to moderate. Okay, let's look at some of the other features. For the ionized metals, those ionized metals, that's this H and K line. Those are really strong. These downward spikes are very large, so I'd say this is definitely strong. And for the neutral metals, well, we've got a little bit of a downward spike there, a little bit more of a downward spike there. I'm probably going to put that as weak. So again, our goal here is to go through the graph, identifying some of these common spectral lines, and determining whether those particular features are strongly showing up, so large downward spikes. Are they just small downward spikes, so they're just showing up a little bit? Or are those, at that part of the graph, is the graph no discernible downward spike? Notice there is always going to be a certain amount of noise in that data. So if you can't tell whether it's a downward spike or just noise, basically say that feature's not there. So let's put this together. We just said that our strongest feature was the ionized metals. We have to have a certain situation where those ionized metals are going to be pretty strong. So on this graph, we can say it's going to be one of the spectral classes where those ionized metals are strong. We can kind of start narrowing this down. For the hydrogen features, those are going to be kind of weak to moderate. So right around here is where those hydrogen features are weak to moderate. And the neutral metal line, well, those are a little bit weaker, so maybe kind of a little bit further on that side. So we want to identify what vertical line, what spectral class seems to match all of that data. We have strong ionized metals, kind of medium hydrogen lines, and weak neutral metals. And again, we also have a kind of medium temperature. So I'd put this probably at a hot type G or a cool F. I think this one ends up being a G-type star, but yeah, I'd say between a hot G star or a cooler F star. And that's the way that we are going to identify, jump ahead here, get rid of some of these things. So I'll erase some of those features that we were drawing. So this one, again, is a spectral type G. It's got those really strong features from ionized metals. So we know that that has to be pretty strong. It's got moderate hydrogen lines in there and weak neutral metal. So I would put this at, again, probably a hot G or a cool F for this one. So this is the technique that we're going to use for, we're basically going to go through the rest of this class, going through more examples of this and identifying what spectral type we have for each of these particular stars. Let's try this one. Here is a new star, and I'm going to clear my previous notes. So again, I really do like this setup. When you're going through this yourself, have this picture beside you. It will be given to you on the test. And say, from Wien's law, what are we getting for temperature approximately? How strong are the hydrogen features? How strong are the H and K lines, the neutral metal lines? And again, we'll talk about molecular bands in a few minutes. So for this one, notice the peak of this graph is even further to the left at shorter wavelengths. In the previous one, the peak was a little bit more to the right at a little bit longer wavelength. This one, I'd say this is going to be a fairly hot star. So let me record that. So this one's going to be hot. And once again, we want to go through some of these features. Let's look at this hydrogen series. Hydrogen alpha, hydrogen beta, gamma, and delta. Not only are these spikes going down pretty far, they're also wider bands. That also contributes to how we define the strength of these absorption features. So this one with these kind of very, very clear, pretty deep hydrogen alpha, beta, gamma, and delta lines, I'm going to say those hydrogen features are strong. So those hydrogen features are strong. So already on this graph, we know we're probably somewhere in here if we have these very, very strong hydrogen features. It's not going to be a G, K, or M because those ones don't have strong hydrogen features. It's probably not going to be a type O because, again, that one does not have any strong hydrogen features when we're looking at, again, this particular line. So we know we're probably in the B to F range for what kind of star we're dealing with. Again, if you zoom in really high in this corner, there's a helium line, there's these H and K lines, and those are all really, really kind of closely packed together. So if we look at those zoomed in, the H and K lines, well, remember in the previous one, let me go back to this previous one, those were really, really low down. But I'd still say that these are probably medium, including the helium line. So let's put ionized metals at medium. So this one is going to be medium. The neutral metals. We've got the sodium and magnesium lines, well, do we really see any features for those sodium and magnesium lines? The graphs will still label where those features would be if those features were present. In this case, I really can't even see whether there are any magnesium or sodium features. It just looks like noise to me. So for this one, I would put none. So neutral metals, none. Okay, so let's see what kind of a spectrum this is. Our neutral metals, there shouldn't really be any neutral metals, so it can't be anywhere in here because there would still be some weak neutral metals. So it's probably, for the neutral metals, it's probably somewhere around here. But we still do have some moderately strong ionized metals. So in this case, if we have pretty strong ionized metals, notice there was also a helium line in there that was also, probably at the medium level. This star is looking like it's probably type A. So again, as we go through this, the game that we're trying to play is looking at each of these features, identifying whether these features are strong, weak, or not there at all, and using that and using this graph to try to identify what is the temperature of this star, what is its spectral class. In this case, with those really, really strong hydrogen lines, none of the neutral metals, moderately strong ionized metals, moderately strong neutral helium, that's probably going to be spectral type A. Now, let's talk about these hydrogen lines in a little bit more detail. Erase that. So we said that for those hydrogen lines, if it's at a low temperature, even though the star is still 3/4 hydrogen, those hydrogen lines are not really going to show up. It's not going to be a very strong hydrogen line at those low temperatures. And the reason for this is that the visible absorption lines of hydrogen occur when the electron transitions from the n = 2 excited state to higher states, or technically I should say when it's in a higher, no, sorry, this was correct. When it starts in the n = 2 state and it absorbs a photon of one of those four common bands, and that excites it to a higher energy state. But if the electron is not already in that n = 2 state, well, it's not going to be able to absorb those specific wavelengths of light. So again, in order for those hydrogen absorption features to show up in the visible part of the spectrum, this set of absorption lines, the star already has to be at a fairly high temperature. That does not mean, again, that other stars are not made of hydrogen. All of these stars, I can guarantee you, this will be a trick question on the homeworks and probably on the test as well. All of the spectra of stars that we're going to look at, they're all primarily hydrogen and helium. Depending on the temperature, that's going to determine whether those hydrogen absorption features are showing up a lot or are not showing up at all. So again, in order for those features to show up, the star already has to be pretty high temperature to get the electrons in that correct starting state. But again, if the temperature is too high, the electrons will be ripped away completely, leaving the hydrogen completely ionized, and there's no other electrons that that hydrogen is going to have. Let's look at this one. Okay. So first, overall shape. Well, if I were to kind of trace out the general outline of this, where the peak of that graph is in terms of Wien's law, that's going to be somewhere over here. That's long wavelength. So what can I say about the surface temperature of this star? Is it going to be a higher temperature or a lower temperature? Yeah. If the peak of the graph is far to the right, then when we were looking at that Wien's law property, if that peak of the graph is further to the right at longer wavelengths, it's going to correspond with a lower temperature. So in terms of Wien's law, this is going to be a lower temperature star. Let's look for some of the common features. So we've got our hydrogen series, and again, we have noisy data. That's always going to be the case whenever we're looking at these spectras, but I can't even really tell what is noise and what might be hydrogen line. So in this case, again, if you can't tell the difference between, oh, there's actually a downward spike there, or it's just noisy data, we're going to say that's there's none of those hydrogen features there. So that one is going to be a none. Let's look at some of the other features. So before we do that, we know that we can't have any strong hydrogen features, which means it's not going to be B, A, or F, probably not G. It's going to either have to be somewhere in this region or somewhere over here, since we're not really seeing any strong hydrogen features. Those H and K lines, well, again, it's kind of too noisy to really say, but I would put that at pretty much none. What about our sodium line and our magnesium line? Major downward spike there, also a downward spike there. That's pretty large. So I'd say that would be strong in this case for those neutral metals. So what we've got so far is it's got to be strong neutral metals, very little, no hydrogen, pretty much no ionized metals, so somewhere over here. There's one more thing about this graph that we want to talk about. Because notice the shape of this graph is a little bit different than the shapes that we've generally seen. There seem to be these parts where there are these kind of large bites kind of taken out of the graph. Those large gaps, those are the molecular bands. So these molecular bands, let's talk about those for just a minute. We said that molecules are groups of atoms held together by chemical bonds. Well, if I have a bunch of atoms held together by chemical bonds, this is no longer one of those low density gases. These atoms are not acting independent of each other. So those molecules have a lot more ways of absorbing and emitting photons. They can absorb or emit photons that cause them to vibrate in different ways. They can absorb or emit photons that change the effect of their rotation. They can absorb or emit photons as electrons jump from one of those atoms to another within the same molecule. So for these molecular bands, instead of seeing very, very thin downward spikes, what we get are these much more wider absorption bands. These things that, again, look like large bites taken out of the spectrum. So if you see those large kind of wide, V or U-shaped sections taken out of the graph, those are going to be your molecular bands. Again, at higher temperatures, those chemical bonds will break, and once those molecules dissociate into their constituent atoms, well, all of those absorption bands are going to disappear. So if we go back to here, these molecular absorption bands, I'd probably put that at maybe medium strength. Again, we'll see some larger ones in a minute. So let's put this at medium. So in terms of identifying what kind of a material we have the strong neutral metals, hydrogen, pretty much none, ionized metals, pretty much none, molecular bands, kind of medium. So I'd probably put this one at either a slightly cool K or a very hot M. I think this one's would be officially listed as a type K star. So again, the game is we've got a low temperature star, no hydrogen features, no ionized metals, strong neutral metals, medium molecular bands. Try to identify what spectral type meets that particular set of criteria. So again, jumping over here, this one is in fact a spectral type K. Let's look at another one. So this one, clear the screen. In terms of just temperature, so this one is jumping over here and probably peaking somewhere far off the graph at longer and longer wavelengths. So overall temperature, what are we thinking? Probably going to be, if it's shifted that far to the side, if that wavelength of peak emission is shifted really far to the right, that's going to be very low temperature. So that would be very low. Well, let's go through the hydrogen series. So let me erase that part of the diagram. Hydrogen series, pretty much nothing. Sodium and magnesium, pretty much nothing. H and K lines, pretty much nothing. So for this one, pretty quick. None of that, none of that, none of that. Molecular bands. Here's where we get those large gaps, significantly larger gaps being taken out of the spectrum. So I'd call those molecular bands strong. So if we have those strong absorption bands, and we again look at what types of features we're getting. So again, strong molecules, not much neutral metal, very low temperature, not much of any other features. That's going to be a low temperature M. Okay. And this would be a particularly cold spectral type M. So again, what this is intended to do is, if we look at the spectrum of a star, we can more accurately determine what is the surface temperature of that star, depending on which spectral features are showing up strongly and which spectral features are showing up weakly. And this method of using the spectral features to identify the temperature of the star, sorry, let me get rid of that part. This is insensitive to that interstellar reddening that we said that Wien's law could be tricked by. That interstellar reddening, if that's applied and you're just using Wien's law, that can throw off your data. But the interstellar reddening will not affect the fact that we can see whether there's a spectral line or not. So what I want to do, just to kind of end this, is do a couple more examples. Maybe I'll actually put that in a separate video. I'm going to do a separate video with a few more examples of measuring these spectral types using the Sloan Digital Sky Survey data set. So I'll put that one in another video if you want to see more examples of that. So just to finish this up, overall, what are the main points that we've talked about? All of these stars, even though they have different spectral features, all of these stars are made of pretty much the same elements in pretty much the same proportion. 3/4 hydrogen, 1/4 helium, 2% heavier stuff. Okay? You're going to see that, you're going to hear that composition quite a bit for the rest of the course. When I looked at some of these stars over here, say, like, let's say this star, oh, it has a really strong sodium line. That does not mean that this star is primarily made of sodium. We don't know of any stars that are primarily made of sodium. What we're saying is, when we see this strong spectral feature from sodium, we're saying that there is at least some sodium there, but this star is at just the right temperature for those sodium absorption features to be very, very prominent. It doesn't mean it's primarily made of sodium. It just means it's at the right temperature for those features to be prominent. This one also doesn't really have any hydrogen features. That doesn't mean that this star is not made of hydrogen. It's still around 3/4 hydrogen. Its surface is just not at the right temperature for these spectral lines to be prominent. So all these stars are made of the same elements in nearly the same proportion. The different absorption lines in the star's spectrum is due to the star's temperature, and we use this OBAFGKM classification scheme to determine those spectral types. And again, when the temperature is right for an element to absorb it, we can identify what that element is based on where those spectral lines are showing up. For example, those hydrogen lines, they show up in a particular pattern. So we can use that to kind of act like a chemical fingerprint. We can identify which spectral features belong to which elements like that. And again, if you want to see some of these spectras yourself, you can go to skyserver.sdss.org. Like I said, I'm going to make another video going through more examples of this sort of analysis using that data. So if you want to see that, then have a look at that next video.